Last time we answered questions about a network exactly by summing the joint over every hidden variable. It's precise. But on a big, tangled model, that sum has an astronomical number of terms, and exact inference simply grinds to a halt. So we change strategy. Instead of computing the answer, we estimate it. We let the network play out over and over, rolling its dice, generating whole random scenarios, and we read the probability straight off how often things happen. Every one of them gives an approximate answer. And the beautiful part is that the more samples we draw, the closer that answer creeps to the exact truth. To see sampling clearly, we'll keep the network as small as possible. Just to yes or no variables. A, which nudges B. A is true 3 times in 10, and B follows A. If A is true, B is true 8 times in 10. If A is false, only 2. And here is the one idea underneath everything. Draw n complete samples from the network. Count how many, call it k, satisfy the event you care about. Your estimate of that event's probability is simply k over n, a frequency. As n grows, that fraction settles onto the exact probability, the law of large numbers, quietly doing our work for us. Small n is noisy. Large N is trustworthy. The simplest recipe is prior sampling, also called direct sampling. Walk the network top to bottom, in topological order, parents before children. At each node, flip a weighted coin from its table. Sample A. First, then use A's value to sample B. Let's actually run it and drop each finished sample into one of two bins on the right. Did it come out with a true or a false? Watch the counts build. Sample 1. A comes up true. Then B true. Into the true bin. Sample 2. A false. B false. Sample 3. A true again. Keep going. 4. A false. 5. A true. 6. A false. Each complete row is one honest draw from the network's own distribution. 7 samples in. And rather than let the list march off the screen, we just read the bins. 4 landed with a true, 3 with a false. Divide, and you already have an estimate of A's prior, 4 out of 7, about 0.57. The true value is zero point 0.3. We're way off because 7 is a tiny sample, but every extra draw tightens it. Let's watch that promise play out, this time chasing a real posterior. The probability A is true, given we saw B true. Exact inference pins it at 12 over 19, about 0.63. That gold line is the truth we're aiming for. Now let the estimate run. At 10 samples, it staggers around, wildly high, then low, nowhere near the line. That's the noise of a small sample. The variance is huge. But push n up. 100 samples, 1,000, 10,000, and the wobble shrinks. The estimate stops wandering and locks onto the gold line. That's the law of large numbers made visible. More samples, less scatter. Here's the whole calculation on one slide. Say we kept 1,000 samples that match the evidence. Be true. Of those, 632 also had a true. The estimate is 632 over 1,000, 0.632. And look how close that lands to the exact 12 over 19, 0.6316. With 1,000 samples, the estimate is essentially the answer. Prior sampling gives us marginals for free, but usually we have evidence, and we want a conditional rejection. Sampling handles that with a blunt rule. Sample the whole network as before, and the moment a sample disagrees with what you observed, throw it away. Keep only the ones that agree, and count within those. Let's run 10 samples, looking for a given B true. Here they are, 10 complete draws of A and B. The evidence we need is B true, highlighted in gold. Now apply the rule. 3 of these samples came out with B false, numbers 2, 4 and 8. They contradict the evidence, so out they go, struck through and wasted. 7 samples survive. Among the 7 survivors, How many have a true? Numbers 1, 6 and 9, 3 of them. So the estimate is 3 over 7, about 0.43. 0.43, when the true answer is 0.63. That's just small sample noise. 7 kept samples is far too few. But feel the deeper problem. We generated 10 and threw away 3. When evidence is rare, almost everything gets rejected, and rejection sampling becomes painfully wasteful. Rejection wastes samples. Likelihood weighting refuses to throw any away. The trick: don't sample the evidence at all. Just clamp it to what you observed. Sample only the other nodes. Then, to stay honest, weight each sample by how likely the evidence was, given the values you drew, the product of the evidence tables. To see the weight as a real product, take a network where a feeds to evidence nodes, B and C. Both observe true. We sample A, then weigh in both tables. Suppose this sample drew a true. The evidence weight is the chance of B true given a true, times the chance of C true given a true. zero point 0.8 times 0.6, which is 0.48. One number that says, this sample supports the evidence fairly well. Now the full estimate. Back on the A to B net, with B clamped true, we sample only A each time, and its weight is B true. Given that A, here are 5 samples. A true weighs 0.8, a false weighs only 0.2, because a false A makes the observed B far less likely. Instead of counting samples, we sum weights. Add the weights where A is true, the 2.8s for 1.6. Add all 5 weights for 2.2. Divide the weighted true mass by the total. 1.6 over 2.2, which is 8 over 11, about 0.73. Every sample counted. Nothing was thrown away. One warning worth burning in. If you just counted the samples, 2 of 5 had a true, you'd say 0.4. That's wrong. It ignores the weights entirely. In likelihood weighting, you must always use the weighted sums, never a plain count. And a caution for later: when a network has many evidence variables, those weights multiply into tiny numbers. A few samples dominate, and the estimate gets noisy again. Likelihood weighting helps, but it isn't a cure-all. There's a third idea, and it's the workhorse behind real tools like STAN and PYMC. Gibbs sampling, a Markov chain Monte Carlo method. Instead of drawing a fresh sample from scratch each time, it edits one it already has. The magic is that to resample one variable X, you don't need the whole network, only its Markov blanket. That's X's parents, its children, and its children's other parents. Given that little shell, X is independent of everything else, so each step is cheap. Pick a non-evidence variable, look only at its blanket, and redraw it from that local distribution. Do it thousands of times, and the samples form a chain that provably converges to the true posterior. One honest catch: the chain starts from a random guess, so its first samples are junk. They reflect where it began, not the true distribution. We throw those early ones away. That discarded stretch is called burn-in, and only then start collecting. Your turn. 2 quick ones. First, the frequency. Of 500 kept samples, 300 have X true. What's the estimate? Second, a weight. With B and C both observed true, a sample draws a false. Given those two evidence tables, what weight does this sample get? Pause and work both out. Here's the check. Part A is a plain frequency. 300 over 500 is exactly 0.6. Nothing fancy, just K over N. Part B is a weight. The product of the two evidence tables at the sampled AB true given a false is 0.2. C true given a false is 0.1. Multiply. 0.2 times 0.1 is 0.02. A tiny weight, because a false makes both observations unlikely. If you got both, you've got sampling. Trap 1. rejection sampling, and rare evidence. If what you observed is unlikely, you'll throw away almost every sample, and the few survivors give a shaky estimate. Reach for likelihood weighting instead. Trap 2. Forgetting the weights. In likelihood weighting, the answer is a ratio of weight sums, not a count of samples. Count naively and you get the wrong number. Every time. Trap 3. What more samples fix? Drawing more reduces the random scatter, the variance. It does not remove bias. A biased sampler just converges smoothly to the wrong place. And trap 4. Order. You must sample in topological order, parents before children, so every node has its parents' values ready. Sample out of order and the numbers are meaningless. Let's lock it all in. When exact inference is too big, we estimate. Draw n samples, count k matches, and k over n converges on the true probability. Rejection sampling is the plainest. Sample from the prior and discard anything that clashes with the evidence. Simple, but wasteful when evidence is rare. Likelihood weighting is the smarter cousin. Clamp the evidence, sample the rest, and weight each sample by the product of the evidence tables. No sample is ever wasted, and Gibbs sampling is the industrial workhorse. Edit one variable at a time using its Markov blanket. Let the chain burn in, then collect. When exact inference gives up, sampling carries on.